Welcome to part 5 of the integration topic. In this video we're going to be focusing on the chain rule. So first, before we get started on the integration side of things, let's do a little recap of differentiation with the chain rule. So let's say we have some function y equals ax plus b, and that's all to the power of n, and we want to find dy dx. Well, looking at this, we might say this is a bit complicated, so I want to replace this ax plus b, this bit here, I want to replace that with another variable, and we'll call that u. So we're going to say, okay, let's do a substitution. We're going to let u equal this ax plus b. So then what do we have? Well, we have y equals u to the power of n. And now if we differentiate this, dy du, that's pretty easy, right? This is almost as if we would do a y equals x to the power of n, but we're just using a u instead of an x, and so the same rules apply where we bring our power out the front, and then we drop our power by 1. But then of course we go, well hang on, aren't we after dy dx? So we've got dy du, that's not the same thing. So this is where we can say, alright, well let's go back to our substitution, and we've got u in terms of x. What's the derivative du dx? So just focusing here, we can see that the derivative of u with respect to x is simply a. And now we can do a cool little trick where we can combine du dx and dy du. If we treat them just like fractions, we can say that dy dx is equal to dy du times du dx. Because notice that the du's just cancel, right? So this is equivalent. So all we have to do is take dy du, which we have here, and multiply it by du dx. But of course, we don't actually want this variable u in our final answer, because we are just dealing with y and x originally, and u was something we artificially introduced. So let's just undo the substitution, and we have n times by u, but that was just ax plus b, to the power of n minus 1, and then that's all times by a. So that's our derivative. So let's have a look at what's happened, and remember this is just revision, so there is actually a shorter way to do this. But what's happened is the power n has still come out the front, here it is here. Then we have our ax plus b term. The power has dropped by 1. Right, we have n minus 1 now instead of n. And then we also have times by a. That was the derivative of what's inside the brackets. So rather than going through that whole process that we did then, right, that's sort of like the first principles way of thinking about it, but rather than going through that, our shortcut method is just to do what I like to call dob-dib or dib-dob. That is, we differentiate in the brackets, and we also differentiate out of the brackets. So this bit here is our dib, right? We've differentiated in the brackets and got the value of a, and then this bit here is the dob, right? This other bit is the dob. So whether it's dibba-dobba or dobba-dibba, okay, that's a nice easy way to do the chain rule when we see a function like this. Okay, so that's a little refresher on differentiating. But when we anti-differentiate or integrate, we need to undo this process. So let's explore the chain rule for integration. So if we have the integral of ax plus b to the power of n dx, what's going to happen? Well, first of all, we know that we are anti-differentiating. We're doing the opposite process. So let's start with this power. This power needs to be increased by 1. So we have our ax plus b, and instead of n, we now have a power of n plus 1. However, we need to put it over this power. So we need to be over the power of n plus 1. But when we're dealing with a chain rule, that's not enough. Like we saw with the dib-dob, there's differentiating out of the brackets, but then there's also inside the brackets. And so when we're integrating, we need to take care of that as well. So we have just taken care of the outside of the brackets part, right? Putting this n plus 1 on the bottom means that if we were to differentiate this, when the n plus 1 comes out the front, it will cancel with this n plus 1, which is good, right? Because looking back here, there's no n plus 1 anywhere. However, if we were to differentiate this expression at the moment, and a, differentiating inside the brackets, and a would come out the front. And there is no a out the front of this. So we need to counteract that as well and put an a on the bottom. Now when we look at this, if we were to differentiate this expression, both the a that comes out the front and the n plus 1 would cancel with these two on the bottom. The power would drop by 1 and we would go back to what we started with. The last thing to remember is our constant of integration that we talked about in the last video, c. And it is also worth pointing out that we can't have n equal to minus 1 on the denominator here, right? Because that would give us a denominator of 0, which is not allowed. So if we have something like this, but the power is negative 1, that's a different type of integration technique that we'll look at in the future. So all that's left to do now is a few examples to wrap our head around this. So number 1, we have the integral of 5x minus 9, and that's all cubed. Now note this is an indefinite integral once again, so we're going to have a plus c at the end of all this. But let's focus on integrating this. So first let's focus on the power. We need to raise that by 1. So we have our 5x minus 9, and instead of to the power of 3, it's now to the power of 4. But then we need to compensate and put this 4 on the bottom of our fraction. But we also need to take into account the derivative of inside the brackets. And in this case, the derivative of 5x minus 9 is just 5. So we need to counteract that as well and put that down here. Here's our plus c on the end. And then to tidy up, we can just see that 5 times 4 is 20. Now, like all integrations, as you get used to them, if you're unsure, just take a moment to look at what you think the answer is and differentiate it. Right, so focus on this line here with me, this first line here that we wrote. If you had to differentiate this, what would happen? Well, first of all, the plus c, that's just a constant, so that would go to 0. The 4 would come out the front, and we would drop the power by 1, so it would become a 3. So the 4 coming out the front would actually cancel with this 4 down here, so they would both disappear, and this would be a 3. So 5x minus 9 to the power of 3, that's looking pretty good, but we've still got this 5 on the bottom. But remember, when we differentiate inside the brackets, a 5 would also come out the front and cancel with this 5 on the bottom. So differentiating this does take us back to the original question. And that's good, right? Because differentiation and integration are opposite processes. So 5x minus 9 to the power of 4 all over 20 plus our constant of integration, that is our answer for example 1. Now on to example 2, which is a definite integral. Right? So we're going to apply the fundamental theorem of calculus rather than having some plus c on the end. Okay, so when we have a square root function, remember it is better for us to to express this as a power of a half. So we have 4x minus 3 all to the power of 1 half. And now let's apply the chain rule for integration. So definite integral, so we bring in our square brackets. We are going to raise the power by 1. So we have 4x minus 3 to the power of 3 on 2. But then we need to put it over 3 on 2. And we also need to take into account this 4. So there is a 4 down the bottom as well. Our lower and upper bounds are 3, or 1 is the lower bound, 3 is the upper bound. But before we go and sub them in, let's tidy this up a bit. Now we've talked previously about how the 3 on 2 on the bottom of the fraction might be nice to flip that around and make it 2/3, but in this particular case, what is 4 times 3 on 2? What's 4 times 1.5? This simplifies quite nicely to be 6. Right, so I would personally just simplify that to be 6 on the bottom. As for the top bit, it's up to you if you leave it as a fractional index, but I'm going to write it as the square root of 4x minus 3 all cubed. So turn it back from fractional indices to using the radical sign. And here's our 6 on the bottom. Okay, so we've simplified it. Now let's apply the fundamental theorem of calculus, where we substitute in 3 and then we subtract what happens when we substitute in 1. So we have 4 lots of x, or 4 lots of 3, minus 3. Now all of this is cubed, as well as being under the square root. And then we take away, and we do the same expression, but now we substitute in 1 for x. Right, so it's a bit messy looking, but just take it one step at a time. Okay, focus on one little bit at a time and it becomes manageable. So 4 times 3, well that's 12. Okay, so we have 4 times 3 is 12, minus 3, okay, well that's 9. So we have the square root of 9 cubed, that's over 6. And then over here we have 4 lots of 1, that's 4, minus 3, well that's 1. So we have the square root of 1 cubed. Okay, what is 9 cubed and what's the square root of that? Now, you might want to rush for your calculator, and that's fine, but remember we can actually do these the other way round. If we want, we could think of this as the square root of 9 all cubed. And what is the square root of 9? It's just 3, and 3 cubed is 27. So we have 27 over 6 minus, hopefully you can see that this is simply 1. 1 cubed is 1, square root of 1 is 1. So we get 27 over 6 minus 1 over 6. And when we combine these fractions, because they have the same denominator, we get 26 over 6. Now this can be further simplified. We can divide both the top and bottom by 2, so we have 13 over 3. And if you like, you could express this as a mixed numeral. This is 4 and 1/3. And there's our answer for our second example.